In this question, we have a signal expressed in the frequency domain that's being passed through a low-pass filter. The low-pass filter has a cutoff frequency of omega radians per second. And the question is, what's the energy that would remain in the signal after passing through the filter? What's the remaining energy after passing through the filter? So what would the filter actually do to our signal? So after multiplying the spectra, you can imagine that wherever the filter is 0, the signal will become 0. So you can imagine that this part of the spectrum from omega radians per second onwards in both directions would become 0. So we would essentially only retain the frequencies from 0 to plus minus omega hertz. So if we wanted to find our energy, again using Parsifal's theorem, nothing would change except we would only integrate from minus omega to omega. So that's the effect of the low-pass filter. The low-pass filter will limit the frequencies and therefore the limits of our integration. So otherwise we would just integrate normally, there's no change. We would carry on calculating EX as you would normally. So it's 1 over 2 pi, the integral of 2 pi e to the minus a omega. Because remember, that's the expression we're given in the frequency domain. Squared d omega. Now, because we have this absolute value, in order to integrate, we need to split the integral into 2. So I'm going to integrate over 2 periods from minus omega to 0, and then from 0 to omega. So it's 2 pi e to the minus a omega, or I should really say minus a minus omega, squared d omega, 2 pi e to the minus a omega, squared d omega. So one of the 2 pi's will cancel, and you end up with an integral from minus omega to 0, 2 pi e to the minus 2 a omega, or I should have said positive 2a omega, plus 2 pi e to the minus 2 a omega d omega. And now it's a straightforward integration. So it's pi over a e to the 2a omega from minus omega to 0 minus, because of that minus, pi over a e to the minus 2a omega from 0 to omega. And that becomes pi over a. Let's do it on a new line. Your final step will be pi over a times e to the power 0 minus e to the 2a minus omega minus e to the minus 2a omega minus e to the power 0. These add up and these add up. So you end up with pi over a 2 minus 2e to the minus 2a omega, which simplifies to 2 pi over a into 1 minus e to the minus 2a omega. So this is our new expression for the energy retained after this double-sided exponential signal in the frequency domain passes through a low-pass filter. So notice how the energy is a function of omega. So what would happen if omega were to decrease? So that means the cutoff frequency of the low-pass filter, if it were to decrease, what would happen to the energy? We would expect it to decrease as well. So Ex is a function of the low-pass frequency cutoff frequency, or the low-pass filter cutoff frequency omega, and that is what we would expect.